Hello, I'm Mark Chenio, IFM Raman Product Manager at HORIBA Scientific. And I would like to thank all the attendees who joined us this afternoon, or whatever time of the day it is in respective part of the world. Today I'll present the results of our efforts at HORIBA Scientific in making NanoRaman an accessible everyday analytical method for chemical-specific nanoscale imaging. I hope that by the end of the presentation I will convince the audience that TERS, and especially its correlation with other SPM modes, is ready to become widely used method in a number of applications in material sciences, chemistry, biochemistry, and so forth. Through the idea of combining two well-known techniques, Raman and IFM, on one side, we have the scanning probe microscope families that are giving us a lot of physical information of the sample surface through the topography, electrical, magnetic, even mechanical properties. But SPM has a drastic lack of chemical sensitivity. That's why we are bringing it together with Raman spectroscopy, which is here really specific in terms of chemical imaging. Raman can provide a lot of structural information through a wide array of applications. But Raman spectroscopy, looking at the nanoscale, has two drawbacks. So first of all, it has a very low cross-section, so understand the Raman signal is something very, very weak. And also it has a limited spatial resolution, which is roughly said the size of the laser spot I'm able to focus onto my sample surface. So by bringing together those two techniques, as I said, we are going to break the well-known Rayleigh criterion by using a real lightning rod effect. As you can see, this beautiful spark on Burj Khalifa in Dubai. In our case, it is a nano-lightning rod effect by using some specific tips onto the IFM side on which we are shining the Raman laser. So those tips playing the real role of nano antenna for both an amplification of the Raman signal, but also a drastic increase in the optical resolution. Raman and IFM analysis can thus be combined on a single microscope system, first of all for colocalized IFM Raman measurement. That's the sequential or simultaneous acquisition of correlated IFM and Raman maps. This is what we can see on this figure with the IFM Raman measurement on a graphene flake. On the top of it, the chemical information with Raman's microscopy is displayed. And on the bottom, the topographic IFM information. All the other SPM techniques can also be done. Let's continue in the present example with the phase imaging here, friction, the capacitance imaging, and the Kelvin probe force microscopy. Thus, chemical properties, thanks to the confocal Raman imaging, that's a diffraction-limited image, are combined with topographic, mechanical, thermal, electrical, and magnetic properties. But what about the sub-micron features? Let's zoom on this small piece of flake that you can see in this blue square with a 3x2 conventional Raman map close here to the diffraction limit. It's difficult to see some details in this image. Then we perform a TERS map of the same area with this specific TERS tips, this nano antenna I mentioned. I will describe it a bit later. The one can clearly see now the graphene edges thanks to the great improvement of the optical resolution, as well as some carbon nanotubes surrounding the graphene oxide flake. So how is it possible? This is the topic of the first part of this talk. To explain that, I will first go through some principles with a brief introduction of TERS and the presentation of the NanoRaman platform. I will then show some application of TERS measurement for the characterization of 1D materials, 2D materials, molecules, semiconducting nanostructures, and biomaterials like nucleobases. Then I will conclude this webinar before answering your question. You'll find a side guide on the left of the slides to help you following the progress of this presentation. A brief introduction to TERS. In tip-enhanced Raman spectroscopy, the Raman excitation laser, number 1 on this sketch, is focused at the tip of an SPM probe coated with either gold or silver, number 2. Matching the wavelength of the Raman laser to the surface plasmon frequency of this noble metal generates an intense localized evanescent electromagnetic field or hotspot at the probe tip, number 3. The field extends only a few nanometers from the tip surface. Since the intensity of the Raman spectra from the sample is directly proportional to the local electric field, bringing this hotspot very close to the sample surface will significantly enhance the Raman signal, often by a power of 10 to the 5 or even 10 to the 6. This electromagnetic amplification of the Raman signal is coming from a lightning rod effect and a plasmonic effect. We thus has 3 factors of influence imposed by this resonance of the plasmon from the TERS tip, which will lay the foundation of the TERS instrumentation. First of all, we have a polarization dependency, which means that the electric field should be preferentially enhanced if the polarization of the laser used is parallel with the tip axis. So when we perform TERS in reflection on opaque sample, the laser should be p-polarized. If you want to perform TERS in transmission for transparent sample, here one needs to use a radial polarization beam. We then have an angular dependency of this enhancement. We have an optimum angle for shining the laser onto the tip apex, which is about 60-65 degrees once performing TERS in reflection. And finally, you have a spectral dependency for this amplification. We should use, as I already said, some noble metal, typically gold or silver, for the manufacturing of the TERS tip. So knowing those factors of influence, now we can build the NanoRaman instrumentation. Let's have a look now at the NanoRaman platform, combining a confocal Raman microscope that you can see on the right, the Explorer from HORIBA Scientific in the present example, together with a scanning probe microscope on the left here, the Smart SPM, formerly ASTNT, now HORIBA Scientific. And in between those 2 instruments in the platform, you have an optomechanical tool to send the laser from the Raman spectrometer to the location at the tip on the IFM side, either from the top for colocalized measurement, but also from the side dedicated for TERS. In both cases, one can use a 100 Hz objective with a numerical aperture of 0.7. So we use some silver TERS probe today, mainly for doing our TERS measurement. Those probes are cantilever-based IFM TERS probes, really easy to use, like every conventional IFM cantilever. This Raman active layer is silver, as I said, with a final protective layer in order to increase the lifetime of this tip. Without it, the lifetime is only a few hours. Silver, as you know, is suffering very quickly from sulfidation, oxidation. But this protective layer drastically increase the lifetime of the tips up to several weeks. We found out a nice enhancement factor with them, up to 10 to the 5 or 10 to the power of 6, and those tips are suitable for top, bottom, and side configuration, both with red and green laser Raman excitation source. We also developed and implement a tool for a very precise laser to tip alignment in this NanoRaman platform. So we are using what we call an objective scanner that is carrying the objective either in the top or in the side illumination. And this scanner is used in XY and XZ direction in order to do a real map of the tip itself before performing a TERS map. So we can see two examples on those figures, XY objective scanner scan and XZ objective scanner scan. That is very helpful to see the location of the hotspot onto the TERS tip and to better visualize the TERS tip vicinity. So thanks to this scanner, we fix very precisely the position of the laser on the tip vicinity. It's providing an easy and precise way for aligning the laser on the hotspot, as I said, and it also provides a long-term stability of this alignment during your TERS measurement. The TERS proof is in the image and in the spatial resolution that can be achieved. The figure that you can see here was collected from a TERS scan, 100 per 100 nanometer scanning area, so it is built pixel after pixel. Here of an isolated carbon nanotube deposited on a gold substrate. So the result is a true TERS hyperspectral image with an optical resolution below 10 nanometer. So this resolution is obtained with the full width at half maximum of the TERS intensity profile across the CNT. So in this TERS map, the red correspond to the pure graphite component of the CNT. This is what we call through what we see through the 2D band, while the white area shows the imperfection in a defect-related area, so that's the so-called Raman D band. And in the red circle that you can see on this TERS figure, I highlight an area in a lattice defect where from one pixel to another, you have two small cross. So from one pixel to another, from the white to the red area, we observe a full decrease in the intensity of this D band. So this illustrates the ability to resolve a chemical signature, thanks to the Raman spectra, down to the pixel step of this map here, only 1.3 nanometer. Let's browse now a couple of applications. It's a non-exhaustive list of applications with results we obtain into our application lab at HORIBA Scientific for the 1D and 2D materials. Conventional Raman is widely used to characterize wide-dimensional structures such as carbon nanotubes, or whether the optical imaging of their nanoscale properties is severely restricted to the optical diffraction limit. A good illustration of how TERS can be used to gain information that would not have been accessible with conventional Raman is presented with this figure. So the map shows the distribution of the intensities of three characteristic Raman bands. You have the D band in blue, the G band in green, and the 2D band in red. The representative spectra are shown on the right. So thanks to a fairly high spatial resolution and a reasonable signal-to-noise ratio, we can identify not only the location of the CNTs on the sample, of course, but also see the difference in the internal structure of those two individual carbon nanotubes based on the variation of the intensity of those characteristic Raman peaks. Thus, in the present example, one can see that the local defects in the graphitic structure are clearly seen in the TERS map. This is the blue spot we have all along the carbon nanotube, and the presence of those defects will govern the electronic properties of the CNTs. TERS studies in the literature for 1D materials such as nanotubes and nanowires concern probing the defect sites, as well as the study of the chirality variation by probing the radial breathing modes at the nanoscale for understanding the transition from semiconducting to metallic behavior of carbon nanotubes. And articles are also being published on pressure-induced Raman shift thanks to the TERS tip at the nanoscale onto 1D materials. Raman signal at the single tube level can be obtained for a better understanding of the quality, the defect density, and the properties in general of the 1D materials, in order to have a better impact on the design of the electronic devices we want to do with such nanomaterials. CNT's article can be found in the literature, as well on silicon, germanium, or gallium nitride nanowires. Let's now have a look at a couple of TERS results applied on 2D materials. The discovery of graphene in 2004 has given a rise to a surge in research activities on 2D materials with novel and exceptional properties. Devices that would implement those 2D materials in modern electronics tend to be smaller than 100 nanometer. Then it is critical to employ techniques that allow for characterization on the orders of tens of nanometer. TERS is a promising technique in that sense, and can be used to characterize 2D materials in terms of size, shape, numbers of layers, electronic properties, and distribution of defects and contaminants. You have the first example here showing the top right, the topographic image, IFM image, on a graphene oxide flake deposited on a gold substrate, and on the left the corresponding TERS map obtained pixel after pixel. Maybe more interesting is the figure D on the bottom right, where we show the distribution of the ratio of the G to D band intensities. This is what is used generally in Raman spectroscopy in order to locate precisely the defects on the graphitic structure. So you have to know that TERS is extremely sensitive to single point defects, and those point defects can be imaged in graphene and in graphene oxide thanks to TERS. This is because the Raman signal of this D band, the defect band, is directly proportional to the defect density you have into the laser spot size probing your sample surface. Through TERS, this probe surface is down to 10 nanometer square. So that's why if we have a defect in this surface, the Raman D band is going to drastically shine. To go a little bit further, other properties than the topography can be mapped at the same location at the TERS image. Other IFM modes, such as conductive IFM or Kelvin probe, might be used to produce images that can be obtained together with TERS. The TERS image here is showing the D band map, and the bottom image the conductivity map of this graphene oxide sample, which correspond to the electric current flowing at the contact point of the IFM tip with the surface sample. In the conductive image, one can observe that the region where the pixels are more intense, corresponding to enhanced conductivity, perfectly matched the folds and the wrinkles of the graphene oxide in bright green on the upper image, suggesting a direct correlation between the conductivity and the TERS signal of the folds of the graphene oxide. This interesting behavior of the wrinkles in graphene oxide sheets led us to investigate whether all the electronic properties of graphene oxide, such as its surface potential, could be linked to the chemical information accessible with TERS. The contact potential difference, or the surface potential, is here obtained with Kelvin probe measurements on figure A. It is showing locally a Fermi level variation that can be put into contrast with the defect density revealed thanks to the TERS map. So here again, we see that we can combine electronic properties through the local conductivity, or here the surface potential map, together with the nanoscale chemical information thanks to TERS. Another example with the TERS map of CVD grown molybdenum disulfide flake, here directly on silicon dioxide substrate. So we have the first TERS image that you can see on that slide, and here the difference in the Raman shift between the E2G and A1G mode is 20 centimeters, -1. So this clearly confirms that the molybdenum disulfide flake is a single layer one. It's important to notice here on 2D TMDCs, the transition metal dechalcogenides, that not only the Raman signal is amplified, thanks to the presence of the silver-coated IFM tip, but also the photoluminescence is enhanced. As you can see here, the tip-enhanced photoluminescence map of the same molybdenum disulfide flake taken simultaneously with the TERS map. It is worth noting that in this nano-PL map, a strong decrease of the PL intensity is observed in the center of the flake. Also reported to some extent in the TERS map above. The nano-PL shift image can also be displayed, showing here a spatial dependence of the spectral shift. We have a strong redshift that you can see in the PL wavelength at the center of the molybdenum disulfide, which is observed. So this truly localized phenomenon can be explained by the presence of an additional layer growth in the center of the flake. And such nanoscale grain, eventually composed of pure metallic molybdenum, can drastically affect the PL intensity. To clearly explain this relationship between photoluminescence intensity at the nanoscale with the surface morphology change, we perform TERS and tip-enhanced photoluminescence measurements on pure monolayer MOS2 flakes and pure bilayer MOS2 flakes, both captured in the same image. We also acquired the Kelvin probe microscopy image of the same area. Figure A is showing the tip-enhanced photoluminescence map, Figure B, the topographic IFM image, and Figure C, the surface potential map. So first, without going into detail, the data confirms the number of layers through the separation of the Raman A1G and A2G peaks, as we see just before on the previous slide. Then you can see a clear difference between the tip-enhanced photoluminescent map and the IFM image in that the B layer, annotated BL in the IFM image figure B, completely disappeared from the tip-enhanced photoluminescent image figure A. And this is consistent with the observation in the previous slide. Finally, the change in the optoelectronic behavior revealed by this tip-enhanced photoluminescence map can be linked to the electronic properties through the surface potential variation that we see in figure C. One can see that the Kelvin probe first map shows positive values for bilayer flakes and negative values for monolayer flakes. So we have a Fermi energy that is increasing in the bilayer molybdenum disulfide flake. Another example with tip-enhanced photoluminescence and TERS characterization of monolayer tungsten disulfide crystallites grown with water-assisted CVD. On the left, the nano-PL intensity, and on the right, the nano-PL spectral energy. As a first observation, with the interior region of the WS2 flake, the nanoscale PL exhibits spatial variation in intensity and in energy that are not correlated with the topography image that you can see very small in the NSAID. The same behavior is observed with the TERS intensity map, with more Raman scattering within the age region. So we have, in a distinct age region of about 110 nanometer wide, we observe a weaker PL, a higher energy PL emission, and a brighter TERS signal. The average TERS spectra of the interior and the age regions are shown in this figure. At the age, the A1G mode is slightly enhanced with respect to the E2G mode. And this is known to be the signature of a smaller carrier density in this area. Also, by looking now at the average deep-enhanced photoluminescence spectra of the central part and the edge of the flake, we can see that the PL narrows and is shifted to higher energy within the edge region. So for the same reason, the smaller carrier density at the edge, and in contrast, we have a larger carrier density in the interior of the flake where more trion emission is seen. Our TERS and tip-enhanced photoluminescence measurement, showing different spectral signatures, as you can see here, revealed once again a nanoscale heterogeneity that is the signature of different doping, different carrier concentration at the nanoscale. The last example of 2D TMDCs, probed with NanoRaman, is a polycrystalline sample of molybdenum diselenide. We first perform an IFM analysis with this 5x5 micron topographic image of a monolayer flake of molybdenum diselenide on silicon dioxide substrate. The quality of the flake is extremely high. As you can see here, the topography is completely featureless in the inner part of the flake. But while probing the capacitance of this flake through the measurement of its second derivative, this is completely another story. We can see here now clearly the grain boundaries standing out extremely well. So let's study now the evolution of those grain boundaries after the transfer of this flake of molybdenum diselenide. Indeed, studying the transfer of 2D materials is crucial for the fabrication of heterostructures based on the stacking of 2D materials. And this also requires an optical characterization technique on the orders of tens of nanometers. So the molybdenum diselenide sample is now transferred from SiO2 to a gold-coated substrate using hot sodium hydroxide and PMMA layer. You have the topography figure A, the Kelvin probe force image figure B, where we see some clear variation of the surface potential again, and the second derivative of the capacitance figure C of this polycrystalline flake of molybdenum diselenide. The capacitance image, showing again more contrast than the topography, reveals some internal features aligned with the crystal edges. So most probably the molybdenum diselenide has been etched away along the grain boundaries. And let's try to confirm that with a TERS map. The TERS map has been done in the white box that you can see on the capacitated image. So on the left, some typical tip-enhanced Raman spectra from this near-field chemical map representing the intensity of the 240 centimeters minus 1 peak in blue and the 340 centimeters 1 Raman band in red. The latter has never been reported in the literature so far. So that's anyway a first and clear indication of nanoscale heterogeneity of this molybdenum diselenide flake. I mean all the red, pink, tiny areas that you can see in the TERS map link to the presence of this Raman band at 340 centimeters minus 1. Then we observed that the TERS of molybdenum diselenide completely vanishes over the regions where we see that the capacitance matches that of the substrate. So no more MOSO2 there. It confirms that the NiOH etches the polymolybdenum diselenide along its grain boundaries. And finally, in the blue spectrum, you can see a new peak, a new TERS band at 995 centimeters minus 1, which is visible and can be attributed to molybdenum trioxide, MOO3. Then nanoscale domains of molybdenum trioxide must exist within the molybdenum diselenide flakes. In the literature, TERS studies on 2D materials have been published on the identification of the defects, point defects, either vacancies or dopants, but also for the study of grain boundaries, of edges, and the induced changes in the optoelectronic properties of those 2D materials, probing the local strain distribution, as well as locally the number of layers, the presence of other nanometric terraces or additional nanocrystals. You have the possibility to correlate Raman and scanning probe microscope other modes at the nanoscale for studying all those nanoscale heterogeneities and having a better understanding of the growth of the 2D materials, once again, to have a better knowledge and study the impact on the design of the next generation devices. Graphene oxide, molybdenum disulfide, molybdenum diselenide, tungsten diselenide, and so on, even heterostructures, has been probed in the literature. Let's now continue by probing, thanks to TERS, just a few molecules. For some application, for example in surface chemistry, in catalysis, in biology, the chemical characterization of molecules on a surface is crucial for understanding their reactivity and function. However, the small quantity of molecules present render their Raman spectroscopic characterization very challenging. So I have an example here with the molecular self-assembly of two kinds of thiol grafted into a gold surface. And we were studying here the grafting substitution in between those two thiols. So first of all, we are using STM TERS tip in the present example to scan and to map the gold sample surface on the left, and then we perform a TERS map, a pixelized hyperspectral TERS map in the square that you can see on this slide. And we can see clearly that the grafting substitution occurs preferentially in the grain boundaries of the gold surface. This is kind of information, again, that is impossible to be obtained with a conventional Raman microscope. TERS can be also used to try as an ultimate goal the single molecular spectroscopy. Indeed, this has fascinated scientists for many decades, and even though single molecule imaging with atomic resolution is achievable using non-contact AFM and STM, chemical information cannot be obtained with these SPM techniques. Single molecule spatial resolution can be achieved in ultra-high vacuum TERS experiments. It has been already published in the literature. But here we wanted to try the possibility of doing that in ambient condition. For that, we perform TERS imaging on fullerenes, both C60 and C70 molecules from a highly diluted solution has been co-deposited onto a gold substrate. So we know that the diameter of the fullerenes is 0.71 nanometer. And remember the chemical sensitivity of 1 nanometer I shown at the beginning of this presentation. It does make sense to try and to think that it might be possible, thanks to TERS in ambient condition, to probe only one of those fullerenes molecules. So we can see on this TERS map that on single pixel, either blue and green, we were able to obtain the unique spectral signature of either the C60 or the C70, not both of them at the same time. And having through the TERS spectra those individual components is a clear signature of this single molecule sensitivity that has been performed here in ambient TERS measurement. TERS studies in the literature concern the single molecule detection, as we saw just before, but also imaging organic molecules and polymer blend in order to study the film morphology and the network. I mean, studying and to be able to distinguish the nanoscopic domains that are interpenetrated at the nanoscale. Other topics like photocatalysis and plasmon-induced catalysis processes are studied in the literature. Thanks to the imaging chemical capability at the nanoscale, in order to study the local order, the molecular orientation, one can have access to the grafting quality and the phase segregation of organic or polymer films. A lot of different organic molecules has been probed in the literature, as you can see. Let's now talk about TERS for probing semiconducting nanostructures. So why TERS? TERS will be used on semiconducting structure to monitor locally the stress or the strain values in order to study the impact on the electronic properties. So as a sample, you have here a silicon germanium nanostripe, which is embedded into a silicon wafer. So we shown on the right with the TERS spectra, the Raman spectrum when the tip is located above the silicon substrate. This is the bottom Raman spectrum. We are located on the base of the very intense silicon phonon band, located at 521 centimeters minus 1. And then on the upper part, we see that when the tip is above the silicon germanium nanostripe, some new bands are amplified and appears. Here we are concentrated onto monitoring the silicon germanium Raman band that is roughly located at 380 centimeters minus 1. So how we have done the measurement? First of all, we use, as usual, the TERS tip for a pure SPM image of the silicon germanium nanostripe, as you can see here. And through one single line, we perform a TERS profile in order to monitor not only the Raman intensity, but in this example, the Raman shift across the stripe. And you can see a huge shift in the Raman band position of the silicon germanium mode between 385 to 380 centimeters minus 1 from the edges to the center of the stripe. And thanks to well-known formulas that can be found in literature, linking this Raman shift with the local strain in the nanostructure, we can calculate the mechanical stress that is about 1.2 gigapascal in the center of the stripe and almost vanishes in the border. So the Raman enhancement in semiconducting structure thanks to TERS help to probe a nano-result value of the stress. And this stress information would be useful, obviously, for studying the impact on the design of electronic devices. More, let's say, conventional semiconducting materials has been probed and published in the literature, not only silicon germanium, but also pure silicon, germanium, and 3,5 components like gallium nitride or gallium arsenide. Let's finish this webinar, this presentation, with one example in life science. The last example of the presentation is related to biomolecules with the TERS imaging of nucleic acids. Here, engineered DNA is deposited on a glass substrate, and an image AFM is shown first. Then a TERS map has been recorded in transmission configuration. This is the only example of TERS in transmission in this presentation, where the signal is collected with an oil immersion objective from the bottom. So you can see this TERS map, order 75 nanometer per 20 nanometers, showing a clear differentiation region with pattern and size, which are consistent with the expected AT and GC homopolyramic blocks. Indeed, we can distinguish on the right the two typical TERS spectra from both the thymine and the cytosine. You have from the left to right the AFM image of the engineering DNA. The two TERS maps from the thymine and the cytosine, as we have seen just before, and the horizontally average map with the color intensity corresponding to those rich regions of 80 on the left, the red one, and GC on the right, the green. The results are very impressive. Plotting this spatial distribution shows a very good correlation with the structure of the DNA. You have the DNA test sequence that is shown on the bottom of the slide. And this correspondence, this very good correlation with the original sequence, is obtained only with minor disturbances that are caused by the drift of the sample, which is almost inevitable at this scale. Here I'm talking about you see the horizontal lines that we can see on the average TERS map. The author of this work also showed a sequence DNA with a resolution down to 3 to 4 bases. So current TERS activities in life science can be divided in two parts: the investigation of isolated biomolecules, amino acid and nucleic acids, and living microorganisms, with the TERS investigation of the cell surface, for example, with high spatial resolution in order to reveal distinct features. So you have a nanometer length scale resolution that can be achieved thanks to TERS. This is a label-free measurement through a real fingerprint specificity for the identification, the detection, and the studying of molecular dynamics. In conclusion, we saw that TERS is a combination between IFM and Raman. More precisely, it's a combination between scattering snow and Raman. It requires a p-polarized light for probing this TERS effect in a side configuration by using some novel metal IFM tip. TERS is done with a NanoRaman platform, and such systems allow colocalized IFM Raman and TERS measurement together with all the scanning probe microscopy modes. Thus, both physical, including electrical, and chemical properties of the sample are probed. We saw that the local defects in 1D materials such as CNTs can easily be probed thanks to TERS. Nanoscale heterogeneities has been revealed through TERS and tip-enhanced photoluminescence on 2D materials. We saw some example of molybdenum disulfide, molybdenum diselenide, and tungsten disulfide. Nanometric terraces, grain boundaries, defects, nanocrystal, and so on can affect the carrier density and thus the optoelectronic properties. TERS and other scanning probe microscope modes, such as scaling probe, capacitance, conductivity, are correlated to link chemical and physical information. Molecules are also probed with TERS down to the single molecule sensitivity. The graphene quality, the segregation, the network can be studied at the nanoscale. The feasibility to measure the mechanical strain in a semiconducting nanostructure at the nanoscale through TERS has been demonstrated. And finally, TERS shows that the signature of distinct nucleobases can be detected, opening up opportunities for label-free DNA sequencing. The possibility to measure other biomolecules and microorganisms is also mentioned. I would like to thank a lot of people from HORIBA Scientific and formerly ASTNT for their work in the NanoRaman platform instrumentation and the development of the application, as well as some collaborators and end users from the academic world. Their name is small on that slide, but their contribution is huge. Please join the IFM Raman and TERS LinkedIn group, on which we regularly publish some news regarding the NanoRaman application and the recently published papers, for example. And if you want to stay tuned and have more information, do not hesitate to stop by the HORIBA pages regarding NanoRaman. Thank you very much for your attention and for following this webinar.